So, what is soil pH?
Soil pH is just a chemical measure of alkalinity or acidity. Low pH soils, say pH 4, 4.5, they can be dominated and driven by things like aluminium or iron in the soil, and that can be a constraint. A lot of plants don't like growing in high aluminium, low pH soils. Likewise, alkalinity at the other end of the scale can be pHs up around 8, 9, 10, and not a lot of plants like growing in that. So when we look at high alkalinity, things like zinc and manganese and things can get caught up, locked up in the soil. So then the plants become deficient in those things. And things like zinc are important because they're involved in root development. And if your zinc's not available, then you get poor root development. pH can be modified by adding things like lime or dolomite, and that can lift the pH of the soils. And so in a conventional system, they'll apply tons of lime or dolomite to shift the pH from 4.5 to 6.5, which is deemed to be some kind of optimum, irrelevant of what the plant actually requires. In the biological system, pH is not so important because within the rhizosphere, the microbes create their own environmental conditions with their pH. So for instance, we might have a plant that wants its root system at pH 6.2. The microbes will then pull potassium into the system, they'll pull magnesium into the system and lift the pH up from 4.5, whereas the outside environment might be pH 4.5. So you can get shifts of about 2 pH units inside a rhizosphere and outside in the bulk soil. Bacteria tend to prefer alkaline soils, and fungi generally prefer more acidic soils. And then they will condition in the rhizosphere what pH the actual plant wants.
So pH isn't just a number, it's the steering wheel of the soil system, and in the rhizosphere, plants are constantly turning it.
That's exactly right. So when a plant or a seed germinates, the microbes form around the developing root system, and they'll create a pH that's conducive to that plant growing. So in agriculture, it's very easy. We might have a lupin that likes growing at pH 4.5, and its rhizosphere is 4.5. So it means that you can go and grow lupins in high pH soils, say pH 7, 7.5, where traditionally in conventional systems you can't. They like acidic soils. And likewise, other plants, they might like growing at pH 6.5, and we're growing them in pH 4.5 soils. The rhizosphere around that root system is then lifted up 2 pH units by the microbes.
So why is pH so important in microbial revegetation programs?
A very good question. Up until now, conventional soil science has really looked just at pH, and we can adjust pH. But pH is only good in a conventional system because we can artificially junk food feed the system, i.e. add calcium, add a lot of lime, add dolomite and so on, add gypsum to get rid of sodium and so on. But that's in an inert dirt, and it's relying on bulk soil changes. EH is the measurement of energy within the soil. So rather than hydrogen ions, we're looking at electrons, and the whole thing that microbes are about are gathering electrons as energy. That's what drives them. So when they go and metabolize some ore, they will be pulling electrons out of the system, and that drives the electrical energy of the system. So EH is the redox potential of a soil. The EH controls effectively what type of bacterial fungi will grow. So if we have a high EH system, we have a lot of oxidization going on. It's a good environmental system for oxygen use and aerobic conditions. And in low EH soils, basically that becomes anaerobic. And root systems don't like growing in anaerobic conditions. So, for instance, we see this when soils get waterlogged, it becomes anaerobic. The EH drops. When it dries out and oxygen can get back into the system, we have a higher EH. So there are specific bacteria that will grow at a high EH, some that will grow at moderate EH, and some that will grow at low EH. The problems with the low EH ones are that they're the denitrifiers, the ones that break down nitrogen. There are sulfide bacteria that release hydrogen sulfide, and there are methanogens. So these are not particularly nice microorganisms in the root zone, whereas at a high EH, they're the decomposers, the aerobic nitrifiers. They are involved in carbon, nitrogen, sulfur cycling, right? So that's with the bacteria. Fungi tend to be middle of the road. They tend to like a moderate EH. So the sweet spot for fungi is in that middle of the range thing. So if you have a low EH system, you tend to drive it towards bacterial dominance. If you have a middle of the road EH, you're driving it towards fungal dominance. And that's what we want in our biological systems, because 80% of flowering plants on this planet are fungal-dominated plants. They like to have fungi in their root zone, like the mycorrhiza and so on, with some bacteria. When we go on to newly developed construction sites or mine sites, any rehabilitation sites, we generally find that there are very poor levels of EH. They're low. And so it's dominated by bacteria. And what happens is, as we develop the biogrowth system, we start shifting the EH up, and that then helps the fungi develop, and we start creating a more living, dynamic soil. Once the fungi and the mycorrhiza grow, we get better input. When we get a middle of the road system, when we get a middle of the road EH, mycorrhiza and other fungi tend to dominate, and they pull in nutrients and water into the plant from a distance. And so the plants benefit from this middle of the road EH. If it gets too high, it can be actually detrimental, so it can be oxidizing, but very rarely do we see that.
So microbes are the engine. EH, pH tells us if they've got enough fuel to build soil, or if the system is running flat.
That's exactly right. So what we want is a general balance of pH. So the microbes in the rhizosphere will create the optimal pH for that plant that they're hosting, and the EH will be set basically to drive it towards a fungal dominance or bacterial dominance, depending on what the plant type is.
So why is pH adjustment less critical in a microbial program like the biogrowth program than a conventional program?
Yeah, very good question. The whole thing with the chemical approach to fertilizer is we use chemically solubilized fertilizers like NPK. And what happens is that by solubilizing it, they wash through with water. And basically, there's very poor nutrient use efficiency with the macronutrients. One of the big problems with things like phosphorus is that they can very easily be locked up in the system. So if there's aluminium in the soil or high levels of calcium, you can lock up phosphorus and it becomes unavailable for the plant. So to adjust that, we chemically change the pH, and that releases the phosphorus. So in aluminium-dominated soils at pH 4.5, we'll go and put a couple of tons of lime on, lift the pH up to, say, 6.5, and that will release the phosphorus to the plant. The big problem is that that only releases it close to the plant where the root systems are, right? And we have these nutrient depletion zones. So if you go out about 1 millimetre from a root, basically it can't suck phosphorus in from any further out. So if you've got phosphorus at a distance, it's not available to that root. Likewise, nitrogen is more mobile, and it can be sucked in from about 1 centimetre away from the root. That's in the chemical system. That means that we have to apply more fertiliser. You just put more water-soluble fertiliser on with poor nutrient use efficiency and pull it into plant. We go to the other extreme in the biological system. The system, we don't care about the bulk pH of the soil. So if the soil is pH 4.5, it doesn't really affect the plant because the roots are living inside an envelope or a rhizosphere of beneficial bacteria and fungi, and they selectively change the pH around that root system. And so you might find that the root system has a pH inside the rhizosphere of 6.5 when the bulk soil is 4.5. That means we don't have to go and touch the bulk soil. That means we don't have to put huge amounts of input in, and we're not ultimately creating nutrient excess which can pollute the environment.
So microbes buffer the soil. They make nutrients available across a range, so plants aren't trapped by a single pH number.
That's exactly right. And effectively, the microbes create the rhizosphere and create an optimal pH for that root system.
So when is pH adjustment required in the biogrowth program?
Yeah, another good question. Basically, we should turn it around and say when isn't it required? Mostly in the soils that we're dealing with, they have major constraints like pH. So if they've got very low pH, say around 4.5 or lower, or pH is up 9 and 10, very alkaline soils, we might look at adjusting it. The most important thing about it is that when the rhizosphere forms with the microbes, is they can buffer the system to lift the pH or lower the pH as the plant requires. So only in very rare circumstances will we go and lift pH or lower pH. Most of the time we apply calcium plus because the soil is low in calcium, not because we want to change the pH.
So we don't chase perfect pH. We just create a window where microbes can thrive and they do the rest.
That's exactly right, yeah.